Hello again. In this video, which I'm going to call Kinematics 2, I'm going to be talking about velocity graphically. So if I have a data and I put the time here in seconds and I put position here, which I'll call x, we're just going to go one dimensional. And I'll say that's in meters or centimeters. It doesn't really matter. And let's say I graph position versus time. And this is in meters, right? And I get a linear fit. Looks pretty linear, right? I do the line of best fit and it comes out to be linear. And I calculate the slope and I find it to be 4. Okay, so if you think about the slope is rise over run. So if I do the rise and I do the run, this rise here is nothing other than the change in x. The run is just the change in time to go between these 2 points here, right? Now, if I write that delta x over delta t, that's the actual definition of velocity. So one thing we can say is that the slope in a position time graph represents velocity. Now, let's just say this point here is 2. What this actually means is that when the clock starts, okay, I'm already 2 meters away from the origin. In other words, I did not start at the origin. So let's see if we can write the equation of this line here. So I can say that x, which is position, equals, this is a function of time. That's not a multiplication, just a function of time, is equal to, this is y equals mx plus b. Just the x plays the role of y now. So it's going to be 4 t plus the y-intercept, which is 2. And this 4 here is your velocity. Okay. Now, looking at this graph, I can tell that I'm going in the positive direction because as time passes, my position goes from low to high. It goes from 2 to 3, etc. Right? So now, if I do another, so let's just say this is the velocity of car 1. Well, that's the representation of position versus time of car 1. So if I do car 2, and I come up with a line that looks like this. Let's say it has a slope of, I don't know, 2. Okay, and I start from 1 meter. I can say that car 2 is going slower than car 1 because this line here, okay, this curve in a position time graph is not as steep as for car 1. Now, what happens if I have car 3 starting, starting somewhere between 1 and 2, but going in this direction here. So this is car 3. And it has a slope of 4 in magnitude, but negative 4 because it's slanted down. And this is 1.5. Okay? Now, the speed of car 1 and the speed of car 3 are the same. And the reason for that, because they have the same steepness. It's just that car 1 is going in the positive direction, car 3 is going with the same speed, but in the negative direction. So going forward, if you want to know, if you have to compare 2 graphs and figure out which object is moving faster, just look at the steepness of their curves. And that should do it, okay? So if I have to write the equation for car 3, it should be x as a function of time equals, so it's y equals mx, x, which is time, plus b, which is 1.5. So it just means that if the origin is right where I'm standing, and this is a number line, and you have 1, 2, 3, 4, etc., it means I started 1.5 meters on that side in front of me, and I'm going to start going towards the left here on the board. Okay, so the other thing is not everything goes at a constant velocity. Okay, because here the slope, in the previous one, the slope was constant. It's one line. Well, if I have a curve that looks like, let's just do something like this. Looks like a parabola, right? So it follows y equals kx squared. And this is your position in meters. This is your time in seconds. Let's just say you started at -1. So here you cannot talk about a unique slope because it's not linear. In other words, the steepness changes. So let's say I have, I don't know, this is 3 seconds. If I want to find the speed at 3 seconds, or at least let's just compare the speed at 3 seconds to the speed at 2 seconds. The curve looks much steeper at 3 seconds than it does at 2 seconds. Now, if I want to write the equation of this, this should be x as a function of time. Again, this is not a multiplication, just like when you write f of x in your math classes. It's going to be some constant, k, this is a constant, times t squared, but we're not starting at 0, minus 1. And that's enough to describe the motion of this object. In other words, you can find its position at any time. If I want to find the speed at 3 seconds, I'm looking at the instantaneous speed. I'm looking at the speed at exactly 3 seconds. So in order to do that, calculus is required, but I'm just going to give you an idea of how to do it without calculus. The speed at 3 seconds, which we call the instantaneous speed, then I hope I spelled this correctly, at 3 seconds is basically equal to the tangent, okay, the slope of the tangent to the curve at 3 seconds. Now, what do I mean by that? Well, the tangent is basically, it's a line that touches the curve at 3 seconds, right? And only at 3 seconds. So how do I draw that? Well, when I draw it with a ruler, because we don't have in calculus as a tool, I'm going to draw a line, okay, that touches only at 3, but the space in here immediately to the right and to the left of 3 should be about the same. The angle should be about the same. And I'm sure we're going to make mistakes here because we're just doing it graphically by drawing. Okay, so, but what you need to know is that the speed at a specific moment is just the slope of the tangent at that moment. So if I draw the tangent, all I have to do is to find the speed at 3 seconds. Just take this line, okay, pick 2 points on this line, not on the curve, pick 2 points on that line and find the slope. You can just leave it there. All right, and the last thing I'm going to do is, I'm not actually going to do it. I'm just going to have a problem here for you, and you're going to have to think about it, and we'll discuss it in class. So I need you to come up with some ideas. So 0. So I'm going to draw a number line basically here. So this is -3. And I'm going to look at, if I'm moving to the left, I'm going to see that as negative. It's just a convention. It's a choice. If I'm going right, then that's positive. So if my position increases, no matter where I start, so I can start at -2, but as long as I'm going in to the right on the board, that's considered positive. If I'm going left, that's considered negative. Okay, so I'm going to have 2 objects, one at -3 and one at, this is about 3.5. And this is all in meters. Okay, so I have a car. Okay, don't laugh at my drawings. Car 1, starting at -3, and it's traveling at 2 meters per second. Then I have a car 2, starting at 3.5 and traveling the other way at 3 meters per second. Now, I have 2 questions for you. And I'm not going to write them down. I'm going to just say them. I want you to figure out or create a mathematical model, right? Do this with the math. Don't just guess. And tell me how long, okay, or after how many seconds, okay, will the 2 cars meet? And the second question is, where are they going to meet on this number line? Okay? Now, first you have to write equation for the motion of this car 1, the motion of car 2. Then take it from there and see what you can do. Now, here's another question. This example here that I just did is like assuming that when the clock started, they both get going. Okay. The other question is, when the clock starts, this one goes. Okay? Okay. But I wait a second before I let this one go. Okay? Again, I'm going to let this go when the clock starts. After this is gone for a second, this one starts. So I want you to answer the same two questions I said earlier. So when or after how many seconds, okay, are they going to meet? And where are they going to meet? Okay? And that's it. And I'll see you next time.